Okay, we need to introduce the concept of standard scores, also called Z-scores. A Z-score is a transform number that represents how many standard deviations a raw score is from the mean of its group. So it uses the mean of the group as a standard place. And then it says in lengths of standard deviation, it uses another standard, which is a length of standard deviation. In our previous example problem, that was 2, right? We said it had a mean of 20 and a standard deviation of 2. Well, this Z-score just transforms those raw scores, the scores that we had, 20, 22, 24, 18, 16, turns them into lengths of standard deviations away from the mean. That's all it is. A Z-score is a transform number designating how many standard deviations the corresponding raw score is below or above the mean. Okay, how do we figure out what Z-score is for a particular raw score? Let me show you. So, Z-score is equal to, I don't want to do this. I don't want to put the formula up here because again, the letters make people, they freak people out. Let's just do it. You know what a Z-score is. You know what that is. You know that it means that it's how many lengths of standard deviation a raw score is from the mean of its group. So how many standard deviations is 22 from 20? How many lengths of a standard deviation? In this instance, the mean is 20 and the standard deviation is 2. So how many lengths of 2 is 22 away from 20? Simply, it's one length of 2 away from 20. So a Z-score would be 1. How many lengths of a standard deviation in this context would 24 be from 20? Well, 24 is 2 lengths away from 20. So it has a Z-score of 2. There, you can see that better. 22, it's only one length of 2 away from 20, so it has a Z-score of 1. How about the raw score of 20? How many lengths away is 20 from the mean of the group? That's a silly question. It's no lengths away. It's 0 lengths away, which is exactly why the Z-score here is 0. For 18, it is 1 length less, so it's a -1. Doesn't mean it's bad, it just means what direction is this raw score from the mean of the group. 18 is a -1 Z-score because it's 2 less, 1 length of standard deviation, less than the mean of the group. Similarly, 16 is 2 standard deviations, or lengths of 2, less than the mean of the group. So if we took the mean of the group, 20, and then we went 1 standard deviation length less, 2 standard deviations length less, 2 times 2 is 4, so 4 less than 20 is 16. This has a Z-score of -2. Now you already know what Z-scores are. You understand them. You can see here how they relate to the raw scores. So back here. Okay. Now, I really wanted to make sure that you guys got this. A Z-score formula to find out what a transform number that represents how many lengths of standard deviation a raw score is from the mean of its group is done this way. X minus the mean divided by standard deviation. So X minus the mean divided by standard deviation. X in this situation is whatever raw score we're curious about finding a Z-score for. So X, if we wanted to find out what 22, what the Z-score for 22 is, we could employ X2 is 22, mean is 20, standard deviation is 2. So 22 minus 20 is 2. 2 divided by 2 is 1. If we go back, we can see the Z-score for 22 is 1. Now, if you want to do formulas like this, be my guest. You know, formulas are, I guess people can like them or want to do them, or have fun with formulas. But I wanted you to get what the gist of a z-score is, and that it represents a transforming of a raw score, x, into a z-score that is the lengths of standard deviation the raw score is from the mean of its group. Okay, so we're back to that problem that we had before, which was there's a population with a mean of 20, and we wanted to know what percentage of scores are between 21 and the mean of 20. Well, that's exactly where it should. There we go. How's that? That's a little bit better. Okay. We're trying to figure out what this percentage is here, but we already know what this percentage is, and we know why. Because it's not a rectangular distribution, we can't just split the 34 in half and say it's 17. We have to calculate a z-score for that. So the z-score for 21 is x minus mean divided by standard deviation, or 21 minus 20 divided by 2. We know that the mean for this group is 20 and the standard deviation is 2. So if I do this calculation, 21 minus 20 is 1. 1 divided by 2 is 0.5. So our z-score, the z-score for 21 is 0.5. I'm going to get rid of that. Okay. Get rid of this calculation. And I'm going to put in here the z-scores. So the z-score for 20, which is 0 distance away of standard deviation lengths from the mean, because it is the mean. Well, this thing is all, let's try it again. It's all blurry. There we go. 20 is 0 lengths of standard deviation away from the mean, because it is the mean, so that's got a 0 z-score. 21 is half of a length of standard deviation, which is 2, away from the mean. So 21 is a 0.5, half. 22 we know is 1 length of standard deviation away. So here we've got raw scores on this level, and down here on this level we have z-scores. They correspond to the same numbers, right? The same place. 20 and 0 is saying the same thing. 21 and 0.5 is saying the same thing. 22 and 1 is saying the same thing. Now, we want to know what percentage of scores are between 0.5 and 0. That's where we're going to have to rely on our book. Our book has an appendix to it that has tables. See? Appendix tables. Now, this table chart says a z-score in one column, percent mean to z, and percent in tail. Those are going to become very important for us here. So, what do I do to find out this particular score? I'm going to come in to the table, and I know that I need to find a 0.5 z-score. So I look for 0.5 here. Not here, not here, not here, not here, not here. Oh, there it is. 0.5 z-score. You guys see that? And then it says percent mean to z. That's the next column over. The percent of scores from the mean to the z. The z-score that we have looked at here is 0.5. You'll see that percent of scores from the mean to the z is 19.15. So I know the percentage of scores between 0.5 and 0 z-score for every normal distribution is 19.15. So for us, the percentage of scores between 21 and 20 is 19.15. So here's a question for you. What percentage of scores are above 21? For those of you who have been following along with this entire thing, it'll be easy for you to figure that out. If we know what this percentage is, we know that this is 19.15%. What's beyond that? Well, we also know that from the mean out into infinity is 50%. So 19.15 less is going to be 30.85. So the answer to the what's beyond here is 30.85. Now you could do it that way, or you just look right here at the percent in tail, and you'll see that it says 30.85 right next to the 19.15. See, this book is set up such that it shows you for every single z-score, it shows you the percent from that mean to the z-score, and then from that z-score beyond or out to the tail. That's percent in tail. That's very helpful when you look at these charts and you're going to answer questions like what percentage of scores are from here to there. Okay, we're going to give an example problem for how to figure out the percentage under the normal curve given z-scores for a particular data set. We'll use the example that I have given in one of the PowerPoints, which is, suppose that your friend is a super genius and they have 145 IQ. What percentage of people are actually smarter than your friend? I'm sorry, excuse me, what percentage of people is your friend smarter than? So we're going to draw out first a normal curve. The normal curve starts out here, and we know that the average IQ, or the mean for the population, is 100. Standard deviation is 15. $100, $115, $130, $145. As I count up in terms of standard deviations, we could convert these numbers into raw scores. Or we could also go the other direction if you want. We can do 85, 70, 55. These are the raw scores for IQ. Now, if we want to do the z-scores, the corresponding z-scores, a z-score is just the transform number that represents how many standard deviations these raw scores are from the mean of their group, right? So the relative distances in lengths of standard deviation. This group has a mean, actually I'll do the mu here. So mu just means the population, right? Mu of 100 and the sigma, or the standard deviation, of 15. So one standard deviation less would be a z-score of -1, 2 less, -2, 3 less, -3. The mean of a distribution always has a z-score of 0 because it is no lengths of standard deviation away from the mean, it is the mean. 15 more, or one length of standard deviation more than the mean of the group, from 100 to 15 more, so one length of 15 is a z-score of 1. 2 lengths of 15, so 15 times 2 would be 30. 30 more than 100, or 130, z-score of 2. And 145, that's what your friend has, is 3 standard deviations bigger than the mean of the group. So, what percentage of people score greater than that? We're going to go turn to the back of our books, and I'm going to go find a z-score of 3. So here's the z-score of 3 right here. It says a z-score of 3, I don't know if you guys can see that. Z-score of 3 has 0.13. That's ridiculous. 0.13 in tail. All right. That's 0.13% of people. 0.13% of people is above 145 IQ. So how do we figure that out? We say, well, this represents 100% of people. And the question was asking, what percentage of people are less intelligent than your friend? So all we need to do is take 100%, which is everybody, and subtract from it what is above 145. So 0.13. If we take that away, we'll find it's 99.87. 99.87% of people your friend is smarter than. You have a very smart friend. Bring them to class sometime. It'll be fun. Maybe they'll teach us something. One of the cool things about Z-scores is that it enables us to look at different variables and can kind of compare them to one another. So if you think about that last one we did where your friend had an extremely high Z-score for their intelligence. They had a 3 Z-score. That means they are 3 standard deviations above the mean. And we saw that they're smarter or more intelligent than 99.87% of people. That there's only 0.13% of people smarter than them. That's pretty impressive. But what if you didn't have a really smart friend? What if your friend was really tall? Well, then how would you know how tall you would have to be as tall as your friend is smart? Let's say that the average height for people is 5'8". And let's say that's the mu for the population. 5'8". The sigma or standard deviation for the population, let's say, is 2 inches. So if you needed to be as tall as your friend was smart, you just have to be 6'2". Then you would be 3 standard deviations above the mean. Okay, let's consider the Z distribution. If we take a distribution of raw scores and we convert all of them by taking each raw score, subtracting it from the mean of the group, and dividing it by the standard deviation, we'll get a distribution that looks exactly like the raw score distribution, but instead it has a mean of 0 because the mean is the same thing. It's no lengths of standard deviation away from the mean. It is the mean. We'll have 1 less standard deviation than the mean would be a -1 Z-score. 2 less is a -2. 1 more is a +1, and 2 more is a +2. So Z-scores are transform numbers that represent the length of standard deviations away from the mean of the group that a particular raw score is. So this -1 Z-score has a corresponding raw score that just is 1 length of standard deviation less than the mean of the group that it comes from. The distribution looks exactly the same, but we've converted the raw scores into Z-scores. We can use these Z-scores and the table in the back of the book to find the percentage under the normal curve for any of those Z-scores to 2 decimal lengths. Here's a question for you. What percentage of scores in a distribution are between 0.71 and -0.2? How would you figure that out? The first thing to do is to find where these Z-scores are. So 0.71 is probably right here, 0.71 Z-score, and a -0.2 is just right here. So -0.2. We want to find what percentage of scores are in between those two. So how do we do that? Take the book, and we're going to look up. So go to the table where it's table A1. For those of you with this edition, the 6th edition of the book, It's on page 671. Unless you have the international version, then it's a little different. So what we're going to do is find first the z-score of 0.71. So I have to flip to the next page, and on the first column of z-scores on 672, you'll see the z-score corresponding to 0.71 says that the percent of scores from the mean, 0, to the z is 26.11. Then we're going to go and find 0.2. We'll have to flip back to the first page, and we'll see that 0.2 has a corresponding score of 7.93. You can't see that here, it's too small, but it's 7.93. Now you might say, Professor, I looked at the book and it doesn't have a negative 0.2. Is there some other chart that has a negative 0.2? No. Remember, the normal curve is symmetrical. So the negatives here, the negative here, the negative here, just represent that the raw score is less than the mean. But the shape of the distribution is the same, therefore you can use the shape of this side of the distribution to say what it would be if we had one. If Aaron and Coops published another normal curve table, it would look exactly the same as this one, just with negatives in front of all the z-scores. So you don't need to have a big waste of pages there. You can just say that the same thing would be true for 0.2. The percentage of scores for 0.2 to 0 would be 7.93. So the percentage of scores from negative 0.2 to 0 is also 7.93, almost 8% of scores. Now what we do is we combine those two percentages. So 7.93 and 26.11, we find that that's 34.04% of scores are between a z-score of negative 0.2 and a z-score of 0.71. Let's do another example problem. So suppose that I'm not as smart as your friend. I actually only have an IQ of 105. But I know that that's better than average. I want to know what percentage of people am I smarter than? So I have an average, an IQ of 105. So X in our situation is 105. The population mean is 100, and the standard deviation for the population is 15. So we can draw this out. Average is 100. I'm at a 105. Not 115. That's one standard deviation above the mean. This is 0. So what's the z-score for my IQ? The z-score is equal to x minus mean divided by standard deviation. Note, when we're considering a population with the mu and the sigma, it's the same exact scenario. So if I wanted to find the raw score for population data, I can just say x minus mu and divided by sigma. It's the same thing. So 105 minus 100 divided by 15, that's 5 divided by 15, or 0.3 extending for forever. I go to the book and I look to see what percentage of scores are from 0.33 and above. I'm going to do that one because if I look what percentage of scores are beyond or are percent in tail, I can just subtract that number from 100 and it will tell me what I want to know, which is what percentage of people am I more intelligent than. So how do we do it? We're going to look at this and it says 0.33 z-score. That has 37.07% above it. So above this is 37.07. Now, 37.07 means that that's the percentage of people that are smarter than me. But if I'm looking over here and I see that percentage of people this direction, I want to know what that is. Well, I know that it's not this and that the total thing is 100. So if the total thing is 100, I can just subtract the 37.07 from it, and that tells me that 100 minus 37.07, you can use a calculator for this. There you go. It's pretty easy. 100 minus 37.07 is 62.93. So 62.93 is the percentage of scores that are less than a 105. So I'm smarter than 62.93% of people. Pretty good, but it'd be nicer to be smarter. All right, so that's another example problem of how you would figure out the percent under a normal curve, and you could find someone's percentile rank. Remember, the percentile rank is the percent of people who have less than a particular raw score. So my particular raw score in this sense is 105, and the percentile rank for me is 62.93. That's the percentage of scores that are lower than my raw score. Let's think through another problem with z-scores and another problem with percent under the normal curve. Let's say you wanted to know what are the raw scores that would bound the middle 50th percentile. You wanted to know what was the middle 50th percentile. Well, if we think about what we know about a normal curve, we know that within one standard deviation, that is the 68th percentile. But we're not interested in 68th percentile. We're interested in, can you see that 68th here? No, that's a little too low. Let's go like this. There you go. Okay, we're not interested in the 68th percentile. We want to know what is the middle 50 percentile, or what are the raw scores that would bound the middle 50%, such that 25% is above, 25% is below. This helps us to think about, say, quartiles. Quartiles would be like the 25th percentile and the 75th percentile. That is, 75% of scores are below that, and 25% of scores are below that. How do we figure those out? Well, we go to the back of our book, and we're going to turn to the tables, and we're going to look for where it says 25% in tail, right? Because that's both for 75 and for 25. It's going to be the same percentage. So I've got to look for the percent in tail. Percent in tail, where it says 25. I'm on the percent in tail, and it says 25. The closest I can get is between 24.83 and 25.14, and that's at a z-score of 0.68 and 0.67. Now, here's the thing. A lot of students, you guys think there's a right answer. There isn't a right answer here. There is a right answer. But again, how specific are we going to get? I don't care that you pick 0.67 or 0.68 as a z-score. What I care is that you generally have the concept that that is 25%, that is 25%, and that this middle 50% is what we're interested in finding the boundaries for. That's what I care about. I don't care that you picked 0.67 or 0.68. If you chose either of those, that means you picked 0.67 or you picked 0.68. They're negligibly different from one another. In this sense, we're just trying to get a gist, a sense of it. We don't really need to be as specific as a lot of times students need to. They think there's a right answer. I wish I could get into this with you guys. Maybe we'll do this in a Zoom call, but I often ask students, what is a number? And it turns out they have all these assumptions about what a number is, and yet they haven't defined in their head what it is. So just relax. If you find yourself freaking out that I said it's okay to pick 0.67 or 0.68 as a z-score for these boundaries, you need to relax. Do something to take a big bath or go for a run or have a glass of lemonade or something. Just chill out. Now this 0.67 and this 0.67, I'm going to pick 0.67. If you pick 0.68, that's fine, but I'm going to pick 0.67. This 0.67 and this 0.67 are different in that this one's lower than the mean of the group, and this one's higher than the mean of the group. So this one has a positive z-score of 0.67. This one has a negative 0.67 z-score. So now we know that those are our z-scores that correspond to raw scores. Okay, so if we know this, we know that the z-score is equal to x minus mean divided by standard deviation. We might be asking ourselves, well, how are we going to get from z-score to a raw score? We don't know what it is. We figured out that 0.67 is what bounds the middle 50th percentile, but that's not the question. The question was, what are the raw scores that bound the middle 50%? And so now what we have is this problem here where we have a formula that doesn't give us what we want. What we want to do is find the raw score, but the raw score, x in this situation, is on the wrong side of that. So this requires a little bit of algebra. So if you guys remember your algebra, what we do to one side of the equation, we've got to do to the other. So here's our z equals x minus mean divided by standard deviation. How am I going to transform that? Well, I know z. Z in one of our cases is 0.67, in the other case is negative 0.67. So I know z. I don't need that to be the unknown thing that we're solving for. I need x to be over here. So what do? Well, x is going to be equal to, I'm going to need to get mean and standard deviation away from x so that I can flip the script. So if I want to get rid of a negative mean, I just add the mean. If I do that to both sides of the equation, then it's going to be z plus mean. And over here, I'm also, right, that gets rid of the mean. I'm going to also have to multiply by standard deviation. So if I multiply z times standard deviation, then I get x equals z times standard deviation plus mean. That's going to give us the scores we need. Okay. So if I know now x equals z times standard deviation plus mean, I can plug in these numbers that we had before, where I know what the mean is, I know what the standard deviation is, I don't know what the raw score is. So for us, the mean of the group was 100, the standard deviation was 15, mean is 100, standard deviation is 15, and we wanted to find out what is the z-score, what's the raw score that corresponds to a z-score of 0.67 and negative 0.67. Those are our bounded ones. And the question was, what are the raw scores that correspond to that? Now we have the three elements we need to solve for x, which is the raw score. X is equal to z times standard deviation, or in this case, sigma. Screwed that up there. Sigma plus mu. Again, mean standard deviation for populations. So we don't know what x is, but we're going to first do 0.67. So 0.67 times 15 plus 100. I got to find my calculator here. All right. Okay, Google, what is 0.67 times 15? Nah, it didn't do it correctly. It did it.
857,143.
It screwed it up, so I'll have to do it here, but for myself. 0.67 times 15. All right, plus 100. We get 110.05. 110.05. Ooh. Holding too many things currently. Okay, that's the upper end limit of what we were looking for. The next one I need to do is I need to make it a negative 0.67. So now I'll do negative 0.67 times 15 plus 100 equals, here's a trick for you. It's just going to be 100 less 10.05. So if I do 0.67 negative times 15 it's 89.95. So 89.95 and 110.05, those are our limits for the middle 50th percentile. 89.95, 110.05. That means, and because we're talking about IQ, that 50% in the middle have IQs between 110 and basically 90. So now we've been able to solve another problem looking at Z-scores, how they correspond to the raw score, and then how it corresponds to the percent under our normal curve. So we're still with Z-scores and finding percent under normal curve. Suppose that you wanted to know someone's percentile rank, and then you wanted to see what the Z-score was. You could work backwards. The same way that we worked forwards from a Z-score to the percentile rank, you could work backwards. So let's say we knew that someone had the 57th percentile. This one doesn't work. 57th percentile rank. The 57th percentile rank. We wanted to figure out, well, what's their Z-score? Okay, how many standard deviations above the mean are there? Well, we know that the mu is 100, standard deviation is 15. So now what we can do is go and find in the back of our book, where is 7%? Now, why only 7% mean to Z? That's a great question. The reason that we're only going to do 7% is that we know 50th percentile is the median. The 50th percentile is the median, and so everything below the mean of a normal distribution is 50%. Just like there's 50% above, there's 50% below. Now what we want to do is find out, well, what's this 7%? How do we find where 7% is? And we're going to do that by looking in the back of the book, using our tables again, and finding where percent in tail equals 7. Or I'm sorry, percent in tail equals 43. So percent in tail for 43 is going to be, the closest we're going to get is a Z-score of 0.18. So 0.18 is the Z-score for the 57th percentile. This is another way to figure out percent under the normal curve. We're trying to figure it one way and figure it the other to give you a sense that there are corresponding Z-scores to raw scores, and that those raw scores in relationship to one another can be determined what percentile rank or what percentage people have less than you on a particular distribution in statistics. This is a very helpful thing for us, and particularly when we go to hypothesis testing next, we're going to look at these tails right here. These tails are going to be really important for us, and hopefully you'll be able to utilize the information that we've just learned about Z-scores, percentile ranks, percent under normal curve, and raw scores, how they correspond to a Z-score. Hopefully that will be able to translate into the future when we use hypothesis testing and probabilities. Okay, you have the hardest question now to answer on percentile rank and Z-scores and normal curve. This will be the hardest one. Let's assume that you're taking a test and you know you've got to get to the 70th percentile for you to pass through this. If you don't get to the 70th percentile, you're not going to pass. So how are you going to figure out what the 70th percentile is for this particular group? You know that the group has a mean of 71 and a standard deviation of 5. Now, how are you going to figure out what raw score you need to get? You know it's going to be above 71 because that's the 50th percentile. We know that the mean of a distribution is always the 50th percentile. So here's our mean. We know that the mu, 71. What is going to be the 70th percentile? Well, what we do know is that one standard deviation above the mean, that's the 84th percentile. How do I know it's the 84th percentile? Because 34% of scores are between the mean and one standard deviation above the mean, or the inflection point, and 50% of scores are below. So the percentage of scores that are below one standard deviation above the mean is 84%. If you're getting lost right now, just take a deep breath. What are we trying to do? We've got a test, and we have to figure out what raw score we need to pass this test. And if you don't get past the 70th percentile, you won't pass the test. So we have to figure out what it is. We know the average score is a 71, standard deviation is a 5. So we know that we don't have to get up to one standard deviation above, because that would be the 84th percentile. So somewhere here in between the 50th percentile, which is the mean, and the 84th percentile, which is one standard deviation above the mean, somewhere in there is the 70th percentile. So we have to figure out, well, what's that corresponding raw score to the 70th percentile? How do we figure that out? We're going to take our z-score and find where 30% is in the tail, and then we'll use that z-score to transform it into a raw score given these two things. So we're going to take the back of our book, we're going to again turn to the appendix where it has the tables, and we're going to look for percent in tail 30%, right? If we need to get the 70th percentile, we're going to look for 30% in tail. And I look down here and I see it says 0.52 z-score has 30.15% in tail. So I wouldn't quite be the 70th percentile. So I'm going to go with 0.53, which is 29.81% in tail. So the raw score that I want is something that's going to have a z-score of 0.53. So 0.53 means it's going to be 0.5 of these, right? The z-score is a transform number representing how many lengths of standard deviation a raw score is from the mean of its group. So if I want to know what that x is, the raw score, I'm going to take the z, 0.53, multiply that by the standard deviation, 5, and add to it the mean of the group. That's going to tell me what score I need to get to. So we'll go to the calculator and we'll say 0.53 times 5, order of operations. That's 2.65 plus 71. $73.65. So the number I need to get on this exam is a 73.65. If I get that number, I'm going to pass the class and I will move on. If not, I have a lower percentile rank and I will fail the class. Thankfully, we only have to get a 70% on this class. You don't have to get a 73% to pass. All right. If you can do this problem, you're ready for the exam on normal curve and z-scores.